Hello class, today we're going over Unit 8, Lesson 2. This is 8.2, Transformations of Log Functions. You're going to see this one's very brief today. That's because we've gone over transformations of parent functions so many times that I know you guys know this well. So we're just going to do a brief overview of what it's like to do with log. So remember that the key features of the graph of f of x equals log x. So notice here, when I just say log x, see how there's no base stated? So that implies that there's a base of 10. And remember, when the base is greater than 1, that means that the graph is increasing. Okay. So in this case here, we know that log has a vertical asymptote of x equals 0, right? The parent function for log, we always assume is base 10. And that's what we're going to transform, okay, or usually log of base 10. We know it's going to be increasing, and so what are the key points we use for log? Every other graph we always have key points. So these ones are going to be a bit unique, and you're going to see why I chose these certain x values. So I want you to put these x values into your chart. You do not have to use these, but the reason I chose these x values is because when I do log of these numbers to the base 10 in my calculator, I get nice numbers to work with, or else I'm dealing with decimal numbers. So when I do, enter in your calculator and do log 0.10, okay, and remember in your calculator it's already base 10, you should get -1. Okay, that's a nice point to plot. When I do log of 1 to the base 10, that's 0, and that's because 10 to the 0 would give me 1. Log of 10 to the base 10, that's 1. And then the next number I do is log 32 to the base 10, and that gives us 1.5. Okay, so these are strategically chosen numbers that, right, we keep entering in until we find an easy to plot number. Okay, so this is our graph here. I'll put a little arrow at the end as well here. We've got our vertical asymptote. I know it's hard to plot the 0.10, -1, but you know it's kind of down here a little bit. There's 1, 0, right? And that's always an x-intercept of a log function, as long as it hasn't been transformed yet. And then 10, 1, and obviously the 0.32, 1.5 is off, so we can't really plot that. So that's okay. Just plot as many as you can to get that shape. And remember that the domain of all log functions is XER such that x must be greater than 0. Okay. And the range for all of them is YER. So when we transform a log function with a, k, d, and c, that's what the standard form is going to look like. Okay, so k and d are inside the argument of log. That number 10 may be there or it may not, and then a and c on the outside. So remember, the absolute value of a gives the vertical stretch or compression factor. And if a is negative, then there's a reflection across the x-axis. 1 over the absolute value of k gives the horizontal stretch or compression factor. If k is less than 0, it's a reflection across the y-axis. And we know d is the horizontal translation and c is the vertical translation. Okay, so all the same stuff. Keep in mind that the vertical asymptote will change. Let's highlight that. The vertical asymptote changes when a horizontal translation is applied. Right, so the minute we shift this graph left or right, that means this vertical asymptote moves as well. Okay. So that is when d does not equal 0. The domain of a transformed log function will depend on two things. Where the vertical asymptote has been located, okay, so whether it's been horizontally translated, and whether the function is to the left or to the right of the asymptote. So for example, here the function is to the right of the asymptote. However, if we reflected it across the y-axis, it would be to the left. Okay, so it does depend on those two things. So if the function is to the left of the asymptote, then our domain is going to be XER such that x is less than the d value, so whatever the asymptote value is. And if the function is to the right of the asymptote x equals d, then the domain is XER such that x is greater than the d value. And the range for all the transformed log functions is always going to be YER. So now we're going to describe in words the transformations of the parent function f of x equals log x. So here's our g of x function here. We've been given, you can see it's base 10, so a is 2, k is an imaginary 1, d is positive 3, and c is positive 4. So we're going to have a vertical stretch by a factor of 2. K equals 1, there's no statement that needs to be made. We're going to have a horizontal translation, 3 units right, and a vertical translation, 4 units up. For this function, g of x, the minute you look at it, you should see that it's not in proper notation because the k value has not been factored out. So let's factor out the k value. So we get negative 3 log, square bracket 2, bracket x minus 6, bracket bracket minus 5. So let's start with the negative. That's a reflection across the x-axis. The 3 here means a vertical stretch by a factor of 3. The 2 means a horizontal compression by a factor of 1/2. The 6 is a horizontal translation, 6 units right. And the negative 5 is a vertical translation, 5 units down. All right, so now let's try graphing one using these 4 key points, okay, and the mapping statement. Okay. So let's not forget the mapping statement here. We're going to kind of apply it in the example above. So remember, x, y, the original point, will become x over k plus d, ay plus c. So we're going to transform negative 2 log and x minus 4. All right, so here we can see, okay, that a is negative 2, and k is an imaginary 1, d is 4, and c is 0. So really there's only 2 main things happening here, okay? So always start off with your parent function, which is log x to the base 10 in this case, okay? You're going to write out your 4 key points from the previous page. Okay, so 0.10, negative 1, 10, 10, 1, 32, 1.5. And I always write at the bottom just a reminder that there's a vertical asymptote at x equals 0. So using these transformations, what is the mapping statement going to be? So really we just care about the a equals negative 2 and the d equals 4. So our mapping statement will be xy becomes x plus d, so x plus 4, and then ay, negative 2y. Right? Nothing, right? This would just be divided by k, which is 1, and this would be plus 0 for the c. So that's as simplified as it's going to get. So let's apply that to the table of values here and come up with the new points. So 0.10 and negative 1 is going to become 4.10 and 2. 1 and 0 will become 5 and 0. 10 and 1 will become 14 and negative 2. And 32 and 1.5 will become 36 and negative 3. Note that because the d value is equal to 4, that means that's where the vertical asymptote has shifted. So the VA is now at x equals 4. So let's draw this. And remember here, this indicates that there was a reflection across the x-axis and a vertical stretch by a factor of 2, as well as the horizontal shift 4 units right. So in red there, you should be drawing your parent function for log x base 10. To space it out a little bit, I went up by, I did every 2 squares by 5 on the x-axis. So as we can see here, I drew my vertical asymptote at 4. I plotted my points the best I could. Okay. And you can see that definitely the translation happened. You can definitely see that there was the reflection because now the original was increasing and now the transformed one is decreasing, so it was a reflection. And so that should be our transformed function according to our points. Okay, arrows on both ends. The domain of this has been shifted because of the d value, and because it appears to the right of the VA, we're going to say that the domain is that XER such that x must be greater than 4. And the range, of course, is always YER. All right, so always work with those 4 key points. You can work with some other ones if you want. These ones are just easier to plot, right? Nice numbers. All right, it says here the function log x to base 10 has the point 102. And it says determine the coordinates of the image of this point for the function -3 log 0.5 x plus 2 and then minus 4. Okay. And I'm just going to put in, there should be square brackets here just for proper form to make sure it's enclosed. There we go. Okay, so we have to identify our variables. So we have, or our parameters. A is -3, K is 0.5, D is -2, C is -4. So when we apply it to our transformation statement, we're going to get that xy on the original becomes x over k, so x over 0.5 minus 2, -3y minus 4. I just put over here at the side, you can simplify this even more because that kind of looks ugly. You can write x over 0.5 as x over 1/2, and then obviously you flip and multiply, so that actually becomes 2x. So if you'd like, you can write this on the next line as 2x. Now we're going to plug in 102. Okay. So if you're just going with the form before, that'd be 100 divided by 0.5. If you go in this form, then it's going to be 100, or 2 times 100. Okay, and then minus 2, and then -3 times 2 minus 4. So we get that 100, comma 2, that point becomes 198 -10 on that function. All right, and lastly, it says the log function has been vertically compressed by a factor of 2 over 3, horizontally stretched by a factor of 4, and then reflected in the y-axis. Then it was horizontally translated so that the vertical asymptote was at x equals -2, and vertically translated 3 units down. Write an equation of this transformed function and state the domain and range. So our a value, because it was vertically compressed by a factor of 2 over 3, that means a is 2 over 3. Because it was horizontally stretched by a factor of 4, that means the absolute value of k must be, so here I'll write it the side, so right here, the absolute value of k, okay, must be equal to 1 over 4. Okay. And because it was reflected in the y-axis, that means the 1 over 4 has to be negative. Okay. So k is -1 over 4. Because the asymptote is at x equals -2, that represents the d value, so d is -2. And if it went 3 units down, that means c equals -3. So that means our transformed equation is g of x equals 2 over 3 log, you can put the base 10 if you'd like, square bracket, -1 over 4, bracket x plus 2, close both brackets, and then the minus 3. All right, so we have to consider the domain of this. So we already know that the vertical asymptote is at -2. We just need to figure out if it's on the left or the right side. So because we have a reflection across the y-axis, you can do a little visual in your mind, in your head here, or you can draw it on the side. This is the original, okay? Sorry, let me do this in purple so you know. Okay, so the VA of the new one has become x equals 2. Okay, so this one here is x equals 2. And now it used to look like this, and then it was reflected across the y-axis. So it was increasing before, and now technically it's decreasing. So it exists on the left side, so we're going to say that the domain is equal to XER such that X is less than, okay, to pertain to this side, -2. And of course the range is always YER. All right, as you can see, it's a brief overview of what we already know, just new parent function and points. Good luck with the homework, and let me know if you have any questions.